let's switch to the second topic, which is going to be Gaussian processes and Bayesian optimization. So this one naturally follows. Okay, so this one naturally follows the bandit. So let me share the screen and tell you why. So let's go back to the same slide that we already seen twice about the decision making in microscopy. So notice that the bandit problem addressed the issue of what action can I take. And in the context of electron microscopy, the action can be the type of the detector that you will use. So as you know, I cannot, and this obviously applies in the scenario where I have to choose what action to take because I cannot take action simultaneously. For example, in scanning probe microscopy, situation is very different because in scanning probe microscopy, many of the detection channels can be activated at the same time. For example, if I measure, do the spectroscopy with my probe and I measure current, I can measure electromechanical response at the same time. They don't interfere with each other, and therefore it is not a bandit problem. I can do both at the same time at the same cost. If I do electron microscopy, situation is different. So I can either use the EBS detector, or I can use the EELS detector, or I can use the diffraction, but I cannot do it at the same time. So this is a bandit problem. I need to choose. However, very often we deal with the problems of the optimization in the continuous parameter space. For example, if I deal with the image plane, I need to choose the location for the measurement. So the image plane is the continuous parameter space that has two dimensions, x and y. If I want to optimize the microscope, so we have a duration character. Duration character has multiple control knobs. That's an optimization problem in the parameter space of the settings of the duration character. So in this particular case, if I look at this individual elements, for example, select location or select the parameters of the spectrum, this is a type of problem when we want to do optimization in the low dimensional parameter space. Very important thing is that we are going to talk only about the myopic optimization. So myopic optimization means that the results of my action depends on my prior knowledge, but not on the sequence of the previous actions. Make sense? So simple example, imagine that this is my image plane in the microscope. Imagine that I take the EELS measurements here and here. It's kind of logical that if my sample is beam stable, that the results of EELS measurement here will depend only on what's in this region, but it will not depend on the results of the EELS measurements here and here. So this is the example of the myopic decision making. If my EELS measurement changes the sample due to the beam damage, then the results of the beam measurements here will be dependent on the previous measurements and their sequence. That's a non-myopic decision making. By now, the state of the art is that the community understands myopic Bayesian optimization decision making very well, and pretty much does not understand the non-myopic decision making at all. So let's look at the examples of how it is done. So what is the logic here? What is the intuition? What do we need to know about? Keep in mind that most of the work in this field for the last 5 years has been done in the context of the self-driving lab, like exploration of phase diagrams, optimization of chemical synthesis. By now, there are literally tens of the startups with the round days between 10 and several hundred millions that basically have the business model of Bayesian optimization. And the key thing here, the only additional key thing to know here is that you start with the parameter space, you run some experiment in this parameter space. So for chemists, this would be concentrations or processing conditions. For us, it would be setting on the instrument or the position in the XY plane. So one very important thing that one needs to know is that very often our measurement returns either spectrum or image. So in order to run the optimization, we always need to take our high-dimensional data and use it to define a single or several scalars that we can use as an optimization function. So in other words, we cannot run optimization based on spectra. It's a high-dimensional function. We need to take a spectra and be able to define what is that about the spectra that we care about, like position of the peak, width of the peak, any type of function of the spectra, and that one we can optimize. So as you already by now probably prepared to hear, the definition of the reward function is by now probably 70% of your work. Because if you define your reward function correctly, you're in business, and if not, what you are doing is going to be to work, but even if what you do works, it will not be useful. However, once the reward function is defined, then you fall back on the procedures that are very, very well established, and therefore it's a part of something that can be learned and practiced with ChatGPT or following the examples from detailed courses that we build, not something that you need to spend much time on, or it's more like kind of engineering rather than science at this point. So a very famous type of this type of decision making is the Bayesian optimization. So this, by now in the field of the automated experiment, this is not even 99%, it's probably 99.9%. I know only 4 groups in the world that over the last year started to switch from the myopic Bayesian optimization to the open decision-making processes. So the process has just started. And basically what you need to know is that Bayesian optimization is the myopic optimization process. So this is almost equivalent. So Bayesian optimization can be based on Gaussian processes. However, Bayesian optimization can be based on any model that can give prediction and uncertainty over the parameter space. So very often people talk about Bayesian optimization and Gaussian processes as the same thing. It is absolutely not. So Bayesian optimization is the way how you build the myopic active learning loop. Gaussian process is one of the ways how you can build the surrogate function that can give you prediction and uncertainty. There are many other ways to create this type of surrogate functions. It's just that the Gaussian process somehow become the most famous one. I suspect that the reason why it happened is because they're mathematically very elegant, and also because most of this type of tools are developed from theory community going into experiment, which explains why many of the times they don't work as well as we expect them to work. So this being said, it's absolutely critical to know what the Gaussian process is. And interestingly, this is where the things start to get very closely connected to this whole concept of the Bayesian beliefs and what we know if we don't know anything. So kind of the question of the prior knowledge. So in principle, Gaussian process can be derived in many different ways. So I can, when I teach my course in the spring at UT, I derive it at least in 3 different ways, but I'm sure that it can be done even in more ways. Another very important point is that technically you can use them even without understanding how they work. So I started to use the Gaussian process for automated experiment again in the first year of COVID, because that was the time when the lab was closed and basically I could spend 12 hours a day programming and 2 hours a day playing Doom. But the important thing is that you can use them without understanding. So it took me a year to develop the intuition behind them, and you can move forward and come up with meaningful ways to improve them or use them correctly only when this type of intuition is developed. So in this case, my advice is don't be like Sergey, try to understand first and then use it, because otherwise you will do a lot of things that are meaningless. So anyway, going back to the Gaussian process. So very simple example. Imagine that this is our parameter space. which for convenience is one-dimensional and scalar indifferentiable. This is our unknown function, and we've taken two measurements. So if we've taken two measurements, then if you're a physicist, you will say that we can interpolate them as a linear function. And if you're a data scientist, you're also going to do the same thing. So in this case, data science and physics give you the same answer. So now, imagine that you've done a third measurement, and you got a point here. So the question becomes, what should be the right function, right? So what are our choices? So anyone? Second order, right? So one of the solutions is to say that now we no longer have a line, we can approximate it by parabola. So, okay, the problem is that, imagine that somebody will come and say that, you know what, but I can also approximate it by line. I just assume that our measurements come with the noise. So should we choose the line or should we choose parabola? So remember that a few minutes ago I've showed you the example of the prior belief, right? So Professor Calculus versus John Deschamaux. So the prior beliefs matter, right? So how does it work in this case? It works that if I absolutely believe in data, so my measurements are perfect, there are good reasons for them to be perfect, whatever, and I'm fairly uncertain about the theory, I will choose parabola. If I have a firm belief in the fact that it should be line, it's for whatever physics laws, but my measurements are not perfect, then I will choose the line and say that the deviation of the point from the line is noise. I cannot have the theory and experiment absolutely correct, and they don't match. It's impossible. Now, you can tell me that, okay, are we getting into the solipsistic loop where we have belief in theory, we have a belief in experiment, and we kind of balance them? So how do I know what should I believe in? The answer is based on the prior knowledge. And the most important thing is that this is how the science works. Science is not the set of facts established once and for all. Science is the system of beliefs based on the facts that have been obtained before, and this system of beliefs can change based on what new facts become available. So in the 16th century, we thought that Earth is the state of the universe because it was our belief that human is in the center of the universe, and the sun moves around it. This was a Ptolemaic model. This model was very complicated, and over time, scientists, or humans in general, I mean, those of scientists who was not burned for expressing their opinions not aligned with the preponderant mindset, the evidence accumulated this model is incorrect. So the model was changed from the Ptolemaic to Copernican. Science always works like this. So we always have belief based on the prior knowledge. Based on our motivation and prior knowledge, we come up with experiments. Experiments generate data, then they add to our beliefs, and sometimes we actually go backward and sort of change our models over the significant period of time. So there is a very famous book by Thomas Kuhn, The Structure of the Scientific Revolutions, which basically explains this problem. So remember, most important thing is that scientific knowledge is not immutable, and very often we go back and change it. There are multiple consequences from this. For example, we always believe that science depends on kind of objective, and science does not depend on people. That's not entirely correct. For example, if Einstein has not proposed the general relativity, it is absolutely not guaranteed that it would have been discovered, because experimental evidence available in favor of general relativity has become available only when people work for many, many tens of years to generate it. If there was no driving force for it, it doesn't affect us in real life. So there can be some things like anomalies in the Mercury motion that could be explained away by different methods. If you think that this is a total nonsense, think about it this way. So astronomers are all gung-ho about dark energy and dark matter, right? So it basically says there are things in the world that we don't quite understand, and we try to rationalize them away by assuming that there is a big part of the universe that's not available for observation. I mean, maybe it's true, maybe it's something that we don't understand about the global physical laws, but it's clearly the case when we formulate our beliefs in a way to rationalize things out as opposed to figure out what the things are. So anyway, going back to the automated experiment, this is the example of how we balance the belief in data and belief in perp. So the second thing is that builds a question of how do we build the elementary objects that on the one hand incorporate some set of beliefs and how the system can behave, but at the same time they're most general. So this is exactly what the Gaussian process is. And Gaussian process has a very interesting history because in the old literature they refer to it as kriging. So Krige is the personal name. It accidentally happened to be the name of the person who was looking for gold in South Africa. And as you can imagine, his job was to walk through the deserts, which are not very benign for humans, and dig the holes to find the gold. His obvious task was to minimize the number of the times he digs for gold and there is no return, and find the preferred locations where the gold is likely to be concentrated. So speaking about the incentives, so he clearly had a very strong incentive to develop a powerful mathematical tools to find the gold to optimize function more efficiently, because each round of optimization was literally going in the desert and digging holes. It also probably a certain isolation from other humans kind of stimulated him to come up with the new mathematical concepts. So anyway, what do we do? So imagine that we still have this type of parameter space, but we don't even have any points. It's just we don't have anything. So what can we say about the function over the space? So first of all, the good starting point is that the function should be have one value of y for one value of x. That kind of seems to be natural. Second requirement is that the values of y should have some distribution, right? It cannot be absolutely anything. And then, so this so far are perfectly physically reasonable. So we just kind of introduce the fact that it's physically significant and that we know something about the distribution. And the third element that we need to make in order to go from very undetermined function for something that is better behaved is to introduce the correlations. So all of you know what the correlation is. So for any type of object, you can calculate the correlation function. So basically the assumption that the Gaussian process makes is that we introduce some correlation function that defines the correlation between the values of the function at one point and a different point. So the way these correlations are introduced through kernel, the kernel is basically a function. It can be a Gaussian kernel, meaning the radial basis function. It can be a Mattern kernel, which is kind of much more steep. It can be periodic kernel. It can be pretty much anything else. The important thing is that kernels allow to build the formal algebras on them. So for example, I can build a kernel which is the sum of the Gaussian kernel and the periodic kernel. The important thing is that kernel functional form is fixed. So we choose the Gaussian process based on the form of the kernel. Third point is that at some point, if you just start learning about the Gaussian processes, it's very easy to get swamped under Gaussian. So the choice of the Gaussian function for kernel and the name Gaussian process have nothing in common. So these are they're both Gaussian, but kind of one is Gaussian functional form for correlation function, and another is the general name for the system. It can be kind of misleading. But anyway, so if you choose this kernel, then all of a sudden your functions cannot look like this, but they start to look smooth. So basically you created an object which is all functions that have certain correlation structure, but you don't know anything about the real value. So if you remember the Lewis Carroll Alice in Wonderland, when the cat disappeared and only smile remained, this is almost the same type of process. We took the physical function and we managed to remove all the knowledge about the values of these functions, but we left the knowledge about the correlation between the values. So in some sense, it's very elegant. And it's one of those cases where kind of mathematical objects create the new universes around them. So the Gaussian process is one example, Riemann spaces and so on would be another example, and so on. But for our purposes, all we need to know is that this is how these functions look like. It's very easy to create the examples of these functions. For example, if we change the kernel length, the function becomes smoother. If we increase the kernel length further, then they will become even smoother. So the important thing is this kernel length is a parameter that can be learned during the experiment. And now comes the key part of this whole discussion about how do we use the Gaussian processes to create the surrogate functions. Very simple. So imagine now we talk about the same type of things in terms of priors, data, and posteriors, because now they come back on the second cycle. So prior is what we know before the measurement. So imagine that there have been no other measurements, and therefore our priors are these general Gaussian processes. Or Gaussian process, what I show is several functions sampled from the Gaussian process. So here they have their own priors, for example, noise prior and the kernel priors. So, but this is generally what we have. Now, once we do the measurement, measurement means that we've taken the experimental measurements in the several points, and then we have the values of the function at this point. Let's assume for the time being, so it's easy to relax, but let's assume for the time being that our measurements are precise. And precise means that we know the value of the function at the measurement point exactly. What it means that of all possible functions in the prior distribution, only those that go through the experimentally measured points survive. So all of a sudden, instead of having all possible curves, you have only curves that kind of focused on these specific locations. See? So it's very easy to relax this constraint. So for example, if our measurements come with the noise, we don't have to choose only the curves that go through these points. We need to choose those that are kind of sitting within the noise from the measured locations. And then we do the second step, which is also very elegant, that if we want to create the prediction and uncertainty, much like we did for the bandit, what we do is we simply average all these posterior curves in order to create the average, or it is called the predictive mean, and dispersion. So dispersion means the uncertainty. So you see this trick. It's kind of one of those things that once you understand that, the kind of natural step, oh, I didn't know that I can do things this way. You said that before the measurement, your unknown function can be anything. You say that the only physical constraint you put on it is the fact that it's smooth to following some functional form, but the length parameter is something that you learn during the experiment. Then you take the measurement, and all of a sudden, instead of all possible values, these functions can have the values only those that are consistent with observations. And then you average them, and you get prediction and uncertainty. So this is kind of how it can look like. So the very important point here is that the prediction and uncertainty provides you the indicator of what happens in general, but it's absolutely not equivalent to the mean square error between the ground truth. For example, if the Thiel curve is the ground truth, if the crosses are locations where the measurements are taken, then the blue would be predictive mean, and the red region is the model uncertainty. So notice that the true value is very different from the mean, right? However, the reason why it is useful is because the uncertainties kind of indicate the regions where we should take the next measurement. It's not equivalent, but if we follow this process, then we will discover the true function. Now, how are we going to use this type of construct? So this is the example of the very famous paper by Nando de Freitas, taking the human out of the loop. So 2015. So notice a very interesting thing, that this whole field has been developing like crazy for the last 5 years. But this story is kind of interesting. Before 2010, the only way to work in this field was to graduate in maybe 3-4 groups in the world working in this field. And if you graduate from these groups, your job would be to essentially build a solver, which is a complicated problem. Around 2015, it has become possible to mere mortals to work on it, but still you need to have a PhD in statistics. So in 2019, the code base out there becomes sufficiently developed. So for example, Maxim Ziadinov, who at that time was a staff member in my group, he built one of the first libraries for the Gaussian process-based Bayesian optimization. So that was half a year after GP-torch, but before BOTorch or JAX or AX or any of these things. So over the last 3 years, the frameworks for this type of things are available, actually for the last maybe 5 years. So you can use BOTorch or JAX or whatever. And for the last 2 years, if you ask ChatGPT or Claude to write your code for Bayesian optimization using GP, it will do a pretty good job. But the important thing is that even 6 years ago, you actually had to write your own software to do that. Now you can do that. So this type of tools become available for mere mortals or experimentalists, as it may be, a relatively short time ago. And the rate at which we can use them and make them useful is now limited only by how fast we can learn, not by anything else. So anyway, how do we use it? So imagine that we want to solve the problem of the optimization of this function that's shown in red. We've taken measurement in the black locations, and we calculated this confidence region. So where should we run the next measurement? So the obvious location to run the next measurement is here, because this red function, so this is our expected value, is maximal here. But the second region where it is worth taking the measurement is here, because here the uncertainty is very large. So here we expect good things to happen, and here the good things can happen because we simply don't know much. And this is the idea of the Bayesian optimization. So what the Bayesian optimization does, you start with a surrogate model, you define surrogate model, initialize it, you take experimental data and you calculate the prediction and uncertainty. And then once you have a prediction and uncertainty, you need to make a next step to choose the location for the next measurements, somehow balancing the prediction and uncertainty. So this balancing can be done in many different ways. So this is what is called acquisition function in Bayesian optimization. So acquisition function basically means that I have prediction and uncertainty, and I somehow balance them and fold them together in the single function. So simplest way of doing it is called the upper confidence bound. It's exactly the same upper confidence bound that we had for bandits. So basically what it means, it says I have prediction, I have the dispersion, meaning uncertainty, I'm going to add them together with some proportionality constant, and I'm going to take the measurement where this combined thing is maximum. There are more complex ways of doing it, called the probability of improvement, expected improvement. There are multiple ways how you can create acquisition function based for the novelty exploration, things called knowledge gradients, and so on and so forth. So basically, if you start working with this type of methods, it's worth exploring what the acquisition functions can be. But in general, all of them is balancing prediction of uncertainty in some way. And then the pathway for the Bayesian optimization based on Gaussian processes becomes very, very straightforward. So all you have to do is define your parameter space. So here is one-dimensional, but it can be two-dimensional, eight-dimensional, or it can be even non-differentiable spaces, because Bayesian Gaussian process can work on non-differentiable objects as long as they have a thing called the Borel algebra and Lebesgue measures, but that's kind of applies for molecules, not for experiments. So then you do measurements in two locations here. So you calculate the predictive mean and uncertainty, you combine them in acquisition function, you find the maximum of the acquisition function, you take the measurement at the argmax, you recalculate your surrogate model, you calculate mean and prediction and uncertainty, you recalculate the acquisition function, then you take the measurement at the maximum acquisition function, and then you repeat this process ad infinitum, or as long as you have budget. So this is how the Bayesian optimization works in general. Let me show you a few examples of scenarios when it worked and when it didn't work. So this is a very simple example of using Bayesian optimization for physics discovery. So in this case, the parameter space is two-dimensional. These are the nearest neighbors and the next near neighbors interaction and the Ising model. This is how the ground truths look like. So I can calculate the heat capacity based on the grid measurements. So you can see that heat capacity has maxima at the line corresponding to the phase transitions. So this is how the Gaussian process-based Bayesian optimization look in this case when I run a very greedy algorithm. So very greedy algorithm means that once my algorithm found the maximum, it will explore points around the maximum, but it will generally ignore everything else. So what's good, what's bad? So the good thing is that for this specific problem, this is almost ideal. You see, I kind of discovered my maximum of heat capacity in a very short number of experiments, so I didn't spend any time exploring these regions. That's good. The bad thing is that if there were some maximum here, here, or here, I would never found it, because my algorithm is greedy. It sticks only to the vicinity of the true maximum. So what's my logic for choosing greedy algorithm rather than making it more exploratory? Very straightforward. I have a physical knowledge that tells me that the maxima of the heat capacity should be concentrated in a very narrow part of the parameter space. In other words, I know that there is a maximum, and the maximum stays on the continuous curve. If I didn't have this knowledge, this would be a wrong choice of the algorithm. So what can we use the Bayesian optimization for in microscopy? So this target is the microscope optimization. So as you already get an idea throughout this course is that the starting point is build the interface with the microscope. So for STEM, now we have it. If you don't have AutoScript, then you either need to get AutoScript. If you have scanning probe microscope, basically by now it looks like you have to build the interface. So the technically Bruker and Nanosurf have the Python interfaces. At least Nanosurf, I know that it exists because we worked with this. For Bruker, I don't know what is its readiness state because I never worked with them. For Oxford instrument, we basically had to build our own. But once you build the interface, you can get the data from the instrument and you can send the data to them. But then the question becomes, how do I optimize scanning? So the problem here is that humans somehow are very good in looking at the image and say that this image is good and this image is bad. Machine learning algorithm cannot do that. And then technically it's possible to train the discriminator with the human feedback when the human kind of uses it is almost like a whatever its name, Tinder, I like this data, I don't like this data. But this type of algorithm are not very effective. So what we need to do is to define the reward function. Want to use this one? Okay, you cannot say no to German with the coffee. So anyway, we need to define the reward function. So if we define the reward function, then it is relatively straightforward to optimize the microscope. We just create a Gaussian process-based Bayesian optimization that uses this reward function in order to that's something that we optimize, and the basic principle for the decision making is just GP. So it takes kind of time and effort, but when it works, it's actually pretty interesting, and that does allow us to save time optimizing the instrument. And once it's optimized, we can visualize very complex systems. For example, these are the droplets of water on the substrate. So water is obviously a liquid, but well optimized, the microscope can actually resolve those pretty well. So this is the general idea of the Gaussian process. There are tremendous literature on how this concept can be extended to more complex situations. So these include several kind of axes of development. One is the situation when your measurement noise is non-constant, can change depending on where you are in the parameter space. So the solution for this type of things is so-called the heteroscedastic Gaussian process. Basically what it does, it uses one Gaussian process for the function and another Gaussian process for the noise, and it tries to learn both. So this is the example of how the heteroscedastic GP works. So our data comes with the error bars, which is dependent on where you are in the parameter space. So the Gaussian process doesn't know the error bars. It has access only to the data. It is able to reconstruct the function and reconstruct the noise function at the same time. So the caveat in this case is that heteroscedastic GP are data intensive. So you need to have a lot of data to find out what the parameters are. And it's also sensitive to initialization because it can interpret any noise peak as the true data or as a noise. And the balance between those would be dependent on the initial kernel length. So another example of the way that Gaussian process can be developed is that rather than trying to infer the noise from the measurement, our measurement allow us to measure the noise. So a simple example for that, imagine scanning probe microscopy, where the local spectroscopic measurements can be run fast, but moving from one part of the sample to another part of the sample takes time. So in this case, it is easy for me to run multiple measurements in one location and then average them, gives me mean and noise. And so basically the function and the noise are measured at the same location. And then I can build a Gaussian process that will basically use the measured noise rather than trying to learn the noise. So this is also an example of mix and match approach, where I take some ideas from the Bayesian methods and some approaches, some ideas from the frequency-based methods. So this is an example of the measured noise Gaussian process. So here I measure both the function and the noise, and my process tries to actually simulate them. So it turns out that if you want to do something like this, you actually need to find out what the noise model is, because if you measure noise in the several locations, you need to find a way to extrapolate the noise for the locations where the measurements has not been taken. And again, you can do it by saying that noise function is Gaussian process, or you can introduce some form of the structured equation. For example, you can say that the noise changes linearly inside the system. So the noise can be in the measurement position. So typically we say that we know exactly the point in the parameter space where we are, but we take the measurement with the function with some noise. Sometimes we don't know exactly the position, so we can have a position error. That's called the X noise. If we deal with something like this, then life becomes, so mathematically, you can build the Gaussian process and kind of introduce the correction to the gradient of the function through the Taylor expansion. Practically, you know the principle that differentiation blows up the noise, so small noise start to look much bigger if you differentiate the function. So as the result, the Gaussian processes with the uncertain measurement usually don't work very well. So if things are very, very sensitive to the noise in X. Now, the last thing that I want to illustrate before Professor Duscher postulated the need for break is the structured Gaussian process. So structured Gaussian process have a very interesting story, because kind of at some point, knowing science is not knowing what has been done before, but also knowing what has not been done and why. In fact, it's kind of one of the most important things in order to do something new. So Gaussian processes historically have been developed in the context of the fairly advanced and largely theoretical statistical domains. And if you take any good or most good books on the Gaussian processes, like Roman Garnett, or there are a few good books on the Manning.com, they typically start with a statement like this. They define the Gaussian process. They say that the Gaussian process has the mean function that is 0, and then they start talking, and they also has a kernel function that defines the correlation. And then they start talking about how to construct more complex kernel functions, how to define the Gaussian processes over more complex spaces, how to define the kernel algebras, and so on and so forth. But they will generally say that we consider only the case of the 0 mean function because the mean functions are domain specific. And they're absolutely correct. However, we are physicists. So for us, 0 mean function means that we don't know about anything about our system whatsoever. We based our extrapolations based on the data only. This happens very rarely. Most of the time, we have some idea about how our function can change over the parameter space. So the tricky thing about the Gaussian processes is that they're exceptionally good in approximating functions because their kernel serves almost like interpolation function. So it works remarkably well, but that's an example of the case where something works when theoretically it shouldn't, and it's the wrong thing to do it because it works good on the initial stages, but then things become very, very inefficient. So the correct way to deal with this type of problems is to combine the Gaussian process with the structural model. So practically the way it works is that typically the Gaussian process is determined like this. So you have a normal distribution with a 0 mean and some correlation. So classically, the statistical community takes this to be 0 and says that for the M is the something for domain scientists. So since we are the domain scientists, that's what we need to do. So practically, this is how it will look like. So classical Gaussian process will have a 0 mean, and the Gaussian process defines only deviation from this mean. So augmented structural Gaussian process introduces the probabilistic model for the mean function. So for example, I can say that my mean function is defined like this. So there is some offset plus 2 peaks. The offset has uniform distribution from -10 to 10. This is my prior. The peak shape is Lorentzian, and the parameters of this peak, meaning amplitude, position, and width, also follow some distribution. So notice what happens in this case. So I develop a model which requires a lot of prior knowledge. So it has a structural form, and it has the priors of the parameter values. However, the result of this type of activity is that I no longer deal with the objects that have only information about correlation. I deal with the objects like this, which basically clearly reflect that my function can be anything that has 2 peaks. Make sense? And also this model allows to incorporate the prior knowledge in a very direct way. For example, if I say that this means that my position of the peak can be anywhere between 0 and 1. If I take this distribution to be between 0.2 and 0.3, I can say that one peak can be somewhere here, and another peak can be only somewhere here. So this type of models are more complex, but then they can be made much more specific to specific problem. And this is the example how it works. So imagine that, and the cases where it is useful. So imagine that I want to discover the function that looks like this. So the black line is the ground truth. If I try to do it with a normal Gaussian process, so see how it goes. It cannot find this jump very well because the jump means that the kernel length has to be small. But each time it makes the kernel length smaller, it has to re-examine the different part of the parameter space, because if the kernel is smaller here, then it can be small everywhere else. So if I introduce the structured Gaussian process that is trained for the function that has a jump, then this becomes much more efficient. So in this case, my algorithm finds the jump position very rapidly, and then it spends all the time exploring the tails, but practically I already discovered the function, so there are no surprises here. It works for more complex spaces. So for example, imagine that I want to discover this phase diagram. This is the ground truth image. This is the progression of the experiment. This is the discovery by the standard GP. So we found the bright region, but everything else is kind of horrible. And this is how it will look like if I try to discover it with a structured Gaussian process. So as you see, most of the measurements are spent to localize the boundary, and only few measurements are done here and here. There is a price, because I chose the probabilistic model that says that my function can be only 0 and 1, and there is a sharp boundary between them. So notice that there is practically the value of the function that are not a 0 and 1, and my model kind of threw it away. I could not discover it. But for the features that I put as a part of the model's inferential bias, it worked well. So just the last thing before break, let me illustrate how the Gaussian processes can be combined with the banded type of problem. So this is the type of scenario when you have several hypotheses, and then you need to figure out which of the hypotheses is correct. So how are you going to do that? So let's assume that you have a list of hypotheses, and based on each hypothesis, you can propose an experiment. But if you have 5 hypotheses, each of them proposes different experiment, you need to choose which of those proposed experiments to run. So the way that you do that is you define your initial models, which in the context is the structural equations and the priors. So this is the realization for the ferroelectric domain grows when the models are simply the loss for the domain, possible loss for the domain grows. So then what you do is you choose one of the models to run the experiment, and you see that based on this experiment, how well did the predictive power or predictive uncertainty of each model improve. And then you say that the predictive power of the model is the reward, and then you use the epsilon greedy method in order to choose what is the next model to run. So here we combine two things. One is the physics, the predictive power, and the principles of the decision-making in the bandits, using this predictive power as the reward that we give to the model that defines who gets to run the next experiment. So I've shown you the example of this automated domain growth experiment. The same type of things work for more complex things like exploration of the phase diagrams. And kind of let's stop here and continue after the break.